Thank you everyone for coming to my talk. I wasn't nervous before, but looking at the size of the crowd now I am. Yeah, so let's get into it. So why care about your web server? Because choosing your web server is one of the highest leverage decisions you can make. It impacts performance, the infrastructure cost, and the kind of production issues you see. But there is another lesser known reason this choice is critical. The right web server can provide an elegant solution to problems that are otherwise complex to solve in your application code. My goal today is to give you a framework to navigate these choices so you can confidently select the right server for your needs. We will start with the foundational principles that govern the behavior of modern Ruby web servers. Then, we will analyze Puma to understand its architectural constraints. From there, we will examine two specialized servers, Falcon and Pitchfork, each addressing one of those constraints. We will conclude with a framework for making a decision. Let's begin with the fundamentals. To understand Ruby web servers, we have to start with the global VM lock, or GVL. The GVL ensures that within a single process, only one thread can execute Ruby code at a time. This has direct consequence. If you have a 4-core server and you run only one Rails process, you are utilizing only one of those cores. To achieve parallelism and to utilize all of your hardware, you need to run at least 4 Rails processes. This multi-process approach isn't new. Early servers like Mongrel required running independent processes, which was slow to start and hard to manage. The major evolution was the pre-forking model popularized by Unicorn. The idea is to start one master process that boots the application, and it then forks cheap, fast-starting worker processes. This master worker model is a foundation for the servers we use today. This design provides two fundamental advantages. First, centralized management. The master process can monitor, restart, and manage its workers. Restarting a failed worker is nearly instantaneous. Second, and more importantly, is memory efficiency, enabled by an operating system feature called copy on write. Copy on write is an OS level optimization. When a master process forks a worker, the OS doesn't immediately duplicate all the memory. Instead, they all share the same copy. So if our parent process uses 300 MB to load the app, after forking 2 workers, the total memory usage is still just 300 MB. This is what makes multi-process architecture viable. When either the parent or the child modifies a memory, it becomes private memory. Any new memory allocations done by the processes are also private. Because of this sharing, measuring real memory usage can be tricky. Tools like Top often show RSS or residence set size, which overstays the memory usage by not accounting for shared memory. A more accurate metric is PSS, or proportional set size. We won't go into the details, but it's important to know that this complexity exists when you're analyzing memory usage. That brings us to Puma. Puma builds on the pre-forking model by adding another layer of concurrency, threads. It's a hybrid, multi-process, multi-threaded architecture. As a generalist, it performs well in many scenarios, but it faces challenges at two extremes. Let's examine its first major constraint, which appears under heavily IO-bound workloads. When threads block waiting for database queries, API calls, or file operations, they become unavailable to serve new requests. This effectively reduces your system's capacity even when your CPU resources remain idle. When your system operates near capacity, this leads to a cascade of performance degradation. CPU utilization drops as threads wait, throughput plummets, and the request backlog grows. Your server becomes paralyzed, not from being overworked, but from being stuck in a waiting state. A seemingly intuitive response to I/O bottlenecks is to increase the thread count. This can provide a temporary increase in capacity. However, for a typical mixed workload application, this strategy introduces a new problem. It increases the contention for GVL. Which brings us to constraint number 2, the GVL. As a quick refresher, Ruby's threading model has 3 key characteristics. First, within a process, only one thread can hold the GVL and execute Ruby code at a time. Second, I/O operations are the exception. A thread releases a GVL before a blocking I/O call. And third, Ruby implements preemptive scheduling. So a thread can't hold the GVL for more than 100 milliseconds if another thread is waiting for the GVL. Let's observe how this GVL contention manifests. We will trace 2 requests that in isolation each take 270 milliseconds to complete. Now we'll see what happens when they are processed concurrently by 2 threads in a same Puma worker. Despite both requests having the same individual completion time, the GVL contention creates additional non-deterministic latency for both. The result is a 48% increase in latency for request 1 and a 37% increase for request 2. This is a GVL tax. And it's not a theoretical problem. It has driven major real-world architectural decisions. For instance, the Rails team lowered the default Puma threads from 5 to 3, directly citing this latency impact. Basecamp, prioritizing predictable performance, runs Puma with just a single thread. And Shopify, to optimize for latency, runs process-based servers like Unicorn and Pitchfork. These are major players in our ecosystem, all making a clear trade-off. They're sacrificing some of the benefits of the threaded model to avoid the GVL tax. This is a core constraint of Puma's hybrid architecture. So we have established Puma's 2 challenges, I/O blocking and GVL contention. Let's address the I/O problem directly. What if we used a different concurrency primitive than threads? This leads us to an entirely different architecture in Falcon, which is built on fibers and an event loop. Like Puma, Falcon is a multi-process pre-forking server for CPU parallelism. The key difference is inside each worker. There is no thread pool. Instead, an event loop manages tasks. When a request arrives, it is assigned to a lightweight fiber. There are no limits on the number of fibers spawned. Falcon will spawn as many fibers as there are requests. The power of this model is how it handles I/O. When a fiber encounters a blocking operation, the fiber scheduler automatically yields control, but the worker process itself does not block. The event loop is free to immediately run another fiber. This allows a single worker to handle thousands of concurrent I/O operations. However, this introduces a critical trade-off. Threads are preempted by the runtime. Fibers, on the other hand, are cooperative. They must explicitly yield. A fiber will continue running until it completes, yields, or performs a blocking I/O operation. The consequence is that a single long-running CPU-bound fiber will block the event loop and starve all other fibers. This makes Falcon a highly specialized tool. It is exceptionally efficient for I/O-bound workloads, but it is not designed for CPU-bound workloads. So when should we use Falcon? The obvious answer is for any application with very high I/O usage, anything that spends most of its time waiting for the network or the disk. But the more interesting answer is that Falcon gives us a fundamentally new way to write concurrent code in Ruby. If you have ever looked at event-driven concurrency in Node.js and wished you had something similar in Ruby, Falcon is your answer. This async model, powered by Falcon and the async gem, is exceptionally powerful. It allows you to break long-head Rails rules that were created to work around blocking I/O. For example, the rule never make a slow API call in the controller exists because it would tie up a precious Puma thread. With Falcon, that rule no longer exists. You can make those slow API calls directly and with much simpler code. This approach has tremendous potential. If this interests you, I did a deep dive on both Falcon and async gem last year. So let's reassess. Falcon provides an effective solution for heavily I/O-bound systems. However, it does not address the GVL contention that impacts CPU-bound work. It also doesn't solve certain memory inefficiencies inherent in the standard copy-on-write model. To address those remaining issues, we need to look at an evolution of the pure process model. That brings us to Pitchfork. At its heart, Pitchfork is a direct descendant of Unicorn. It fully embraces the one request per process model. This provides true GVL-free parallelism and outstanding resiliency. But Pitchfork's creator wanted to solve the biggest drawback of this model: memory usage. Let's revisit our copy-on-write example. We have a parent and two fork children with both shared and private memory. The key to Pitchfork's optimization is realizing that private memory isn't monolithic. It has two parts. There is private processing memory for objects in a single request, which gets garbage collected. There is also private static memory, used by the VM for things like inline caches and JIT compiled code. This is a warm-up data that makes a worker fast. And this reveals the critical inefficiency of a standard server. As each worker warms up, it builds this private static block of JIT caches and VM optimizations. Now the crucial point is this: while the content of these caches will be nearly identical across all warmed up workers, the physical memory pages they occupy are not shared. Each worker has to build and store its own private copy. You end up with dozens of processes, all holding identical but separate copies of the same warm-up data. This is a significant waste of memory. It is this precise inefficiency, the duplication of identical but non-shared data, that Pitchfork's reforking is designed to eliminate. Reforking is a core idea of Pitchfork. Once a worker is fully warmed up, it's a perfect template for new workers. Instead of forking from the cold master, Pitchfork can promote a hot worker to become a new mold and fork new pre-warmed workers from it. When reforking is enabled, Pitchfork forks a Gen 0 mold which boots your application. Then the workers are spawned from the mold. Reforking is triggered when a configured number of requests have been processed. When it is triggered, the monitor spawns a Gen 1 mold from one of the workers. Once the Gen 1 mold has started, the Gen 0 mold is terminated. Then, one by one, each worker is replaced by a fork from the new mold. This process repeats for several generations. The result is a cluster where every single worker shares the exact same fully populated caches and jittered code from the moment it starts. Due to an operating system bias on how traffic is distributed, Some workers will handle significantly more traffic than others. Since the criteria for promoting a worker into the new mold is the number of requests it has handled, it's almost always the most warmed up worker that ends up being used as a mold. The result is dramatic. The memory that was previously private static is now shared across all workers. The only private memory each worker needs is for the request it is actively processing. This makes adding more workers remarkably cheap from a memory usage perspective. So, why would you choose Pitchfork? First, it's built on a simple and robust process based foundation. This gives you powerful operational benefits like out of band GC, simpler performance debugging without GVL contention, and outstanding resiliency. If a worker misbehaves, you can simply terminate that one process and it doesn't affect any other requests. Second, Pitchfork builds on that foundation with its unique innovation, reforking. This provides two key advantages. It achieves significant memory efficiency by sharing the JIT cache and other VM artifacts that are normally private. And critically, it delivers a low and consistent latency because reforking ensures every new worker is a perfect pre-warmed copy. Here's the publicly shared data from Pitchfork's deployment on the main Shopify monoliths. They reported a 30% reduction in memory usage. More importantly, they achieved a 9% reduction in P99 latency. These are significant, measurable improvements in a massive scale. Of course, there are some caveats. Reforking isn't enabled by default, and there are few gems which are incompatible. You also have to ensure that your application is fork safe. So to bring everything together, let's look at a decision framework. Each server has its strengths and a set of trade-offs. Puma solves for general purpose concurrency. Its trade-off is a GVL contention and I/O blocking we analyzed. Falcon solves for high I/O throughput. Its trade-off is a cooperative scheduler, which makes it unsuitable for CPU-heavy workloads. And Pitchfork solves for lowest latency and memory usage. Its trade-offs are potentially lower throughput on mixed workloads and the engineering burden of ensuring fork safety. This means that the decision comes down to two questions. First, what is the nature of your workload? Analyze your system's telemetry to understand your actual bottlenecks. And second, what do you value? Is your priority raw throughput, predictable low latency, or absolute resiliency? There isn't a single best choice, but there is a right choice. It's the one whose trade-off you're most willing to accept to solve your specific problems. Thank you. Sorry, I ran through it faster than I practiced. So, since we have a ton of time, like if you have questions, I'm glad to answer.
So you went through your three favorite or the three that you think are appropriate in 2025? There's obviously others around. We got Unicorn or the team I'm using. Team I'm on is still using Passenger. How do those fit into this scene?
I think, like if you're running Unicorn, even its creator has said that it is not actively maintained. If I remember right, like you can run Pitchfork without reforking enabled, and you get a modern web server which is actively deployed and maintained. So, and I don't know anybody who uses Passenger these days. So no answer to that. Yeah.
you gave some numbers around memory gains, efficiency gains. Were those versus base Rails, or were they against Unicorn? Or
So the Shopify numbers, they were running Unicorn before, and the memory reduction and the latency reduction is from running Pitchfork. Yeah. Yes.
Thank you. You mentioned there are some gems that are not compatible with Pitchfork.
Yeah.
Is there anything we should look for gems to know which are compatible, or is there like a list, or is there something they do specifically that makes them incompatible?
Yeah, there is a list. In fact, Pitchfork has amazing documentation. In fact, I think it's one of the best that I've come across all gems, because it specifically tells you, it doesn't try to sell you Pitchfork. It tells you why, if you're happy with what you have, continue with it. And if you have only these specific problems, proceed with it. And it has an exhaustive, it has a list of all the gems that they have found incompatible and which they have also working on making it compatible. So one of the most common one is gRPC, but there exists a fork of gRPC which is reforking safe.
How do you check if your application is fork safe?
If it doesn't have any issues in production, I guess.
And what happens when there is a memory leak and then that process keeps getting forked afterwards?
So one of the reasons why the creator of Pitchfork started this was memory leak in their monolithic application, in the sense that they had already configured to terminate a worker in Unicorn when it breached a certain memory. And with Pitchfork, since everything is shared, the memory usage itself has come down. So if there is a memory leak, that is purely due to that particular request that it is handled. So, and you can apply everything that you apply in Unicorn to Pitchfork. Like you can configure timeouts or kill a worker if it breaches a certain memory and all that.
Yeah. One slightly more tactical question, like how do you, like let's say we want to use Pitchfork or Falcon in our current like Puma, servers or whatever.
Yeah.
How do you even test that? Because like it's like you just deploy Puma and see what happens, or like deploy Falcon and see what happens. I'm certain that's not the answer. Like, is there tooling around? Like, have you guys tactically tried deploying like the same application on two and comparing? Like, did you guys do that?
Yeah, I have deployed Puma and Falcon together, not Pitchfork though. Like what I have done is I'd set up a proxy in front of it and forwarded only certain requests to Falcon, which I knew were IO heavy because they were calling some external APIs and I didn't want to handle that through Sidekick. And when I knew that it was much easier to do in Falcon. But I don't think in that particular case, it would have mattered if the entirety of the application was served by Falcon because we were not really CPU bound. But you can always like deploy the same Rails application in multiple servers and just pass a certain percentage of traffic to it and observe how it behaves.
So thanks for a nice talk. And since Puma is probably fine for most Rails applications, unless there is a GVL contention issue or problem, how would I go about finding out if my application is prone to those kind of things?
A lot of the APM frameworks give you data on that, but sometimes it's tricky. Like I have seen misattributed data, like that the database is being very slow, which I then later realized that it wasn't actually slow, but it was just because of GVL contention that it appeared to be slow. So one of the things that I've done is try reducing the Puma thread counts and see how the application behaves. So if you see a significant increase in performance, that's a decrease in latency, then that means you have GVL contention, which is affecting your application. So you can just start by reducing your Puma thread count. Anyone else? Okay, thank you all.